Hello everyone, I'm Professor Harrison and welcome back to our module on matrix algebra for finance. Today we're covering reduced row echelon form, the full Gaussian elimination procedure, and the three possible outcomes that any system of linear equations can have: a unique solution, an infinite family of solutions, or no solution at all. We'll see exactly what determines which one of these three you end up in. We're following Ruth, a PhD student building out her matrix-based methodology for her dissertation. Today she is wrapping up the solving systems section of her chapter. In the previous video, we saw how she got a portfolio system into row echelon form and used back substitution to find the answers. Today she takes the procedure one step further and finishes the section. Upon doing so, she's going to be able to submit her dissertation for final approval. She turns back to her dissertation chapter. In the previous video, we got an augmented matrix into row echelon form. Then we used back substitution to read off the solution. The full procedure works, but back substitution is a separate manual step on top of the row operations. It ends up being possible to actually fold the back substitution work directly into the row operations themselves. That way the solution just falls out automatically at the end. That's exactly what we're going to do today. The cleaner target form is called reduced row echelon form, or RREF for short. Once an augmented matrix is in reduced row echelon form, the solution is naturally just sitting there in the last column. There's no need for back substitution, no second step at the end, you just read it off. Getting from row echelon form to reduced row echelon form only requires three of the exact same row operations that we've already been using. The full procedure that takes any augmented matrix all the way to reduced row echelon form is called Gaussian elimination. You may also see this called Gauss-Jordan elimination after the two mathematicians who developed it. So let's pick up where we left off last time and finish the portfolio replication problem. The goal of our system of equations was to put some weights into our three assets so that we had the proper exposure to three of our different factors: size, value, and momentum. Our system of equations described how the weight in each of our three assets exposes our portfolio to each of these three factors. The goal is to find out how much we need to invest in each asset to reach our target exposures. In the previous video, we got the row echelon form that we used to back substitute and solve for each of the three weights. The row echelon form was 1, 2, 1, 6, 0, 1, 2, 5, 0, 0, 1, 2. In this row echelon form, the pivots are all leading ones already. This is one of the two conditions for reduced row echelon form. The other condition is that every entry above each pivot also has to be 0, the same way that every entry below each pivot is currently 0. So we need to clear the entries above the third pivot and the entries above the second pivot. What we're going to do is the opposite of last time. We're going to work from the bottom up. The third pivot is 1 in row 3, column 3, and the entries above it are 2 in row 2 and 1 in row 1. To clear the 2 in row 2, we replace row 2 with row 2 minus 2 times row 3. 2 times row 3 is 0, 0, 2, 4. So subtracting that from row 2 gives us 0, 1, 0, 1. Now to clear out row 1, column 3, we replace row 1 with row 1 minus row 3. Row 3 is now 0, 0, 1, 2, so subtracting that from row 1 gives us 1, 2, 0, 4. The matrix is now 1, 2, 0, 4, 0, 1, 0, 1, and 0, 0, 1, 2. The third column now has a leading 1 with zeros to the left and above it. Now we move up to the second pivot. The entry above it in row 1 is a 2. So we replace row 1 with row 1 minus 2 times row 2. 2 times row 2 is 0, 2, 0, 2. So subtracting that from row 1 gives us 1, 0, 0, 2. The final form of our reduced row echelon form matrix is 1, 0, 0, 2, 0, 1, 0, 1, and 0, 0, 1, 2. That is reduced row echelon form. Here, every pivot is a leading 1, and every other entry in every pivot column is a 0. Here's the payoff. The system has effectively been rewritten as three equations. The weight on asset A equals 2, the weight on asset B equals 1, and the weight on asset C equals 2. The solution is sitting in the rightmost column. 2 units of asset A, 1 unit of asset B, and 2 units of asset C will give us exactly the goals that we're aiming for. We didn't even have to do back substitution, we just have to read it right off the matrix. So that is the punchline of Gaussian elimination. Take any augmented matrix and apply these three row operations until it is in reduced row echelon form, and then the answer just falls right out. So what happens when the system doesn't work out this cleanly? When we ran Gaussian elimination on the portfolio system, we ended up with 3 pivots in a 3 by 3 matrix. 1 pivot per row, 1 pivot per column, and everything lined up and the solution came out unique. But that's not the only thing that can happen. To see the other two cases, let's modify Victor's problem slightly. Suppose asset C's factor exposure had been exactly equal to asset A's exposures plus asset B's exposures, factor by factor. In other words, holding 1 unit of asset C gives you the exact same factor exposure as holding 1 unit of asset A and 1 unit of asset B together. When that happens, the third column of the coefficient matrix is literally the first column plus the second column. When this happens, we say the columns are linearly dependent. The reason is that asset C is not adding anything new to the matrix. It's a redundant combination of the other two assets that we already have. So when we run our row operations on the matrix whose columns are linearly dependent, one of the rows will end up collapsing down to all zeros. And what sits in the rightmost column of that zero row decides what's happening next. In the first case, suppose that the zero row also has a 0 in the rightmost column. So you get a row that reads 0, 0, 0, 0. That row represents the equation 0 equals 0, and that equation is true, but it tells us nothing. Effectively, we have 2 real equations for 3 unknowns, which means that the variable is free to take any value and the other 2 adjust around it. So instead of one specific weight on asset C, any weight on asset C actually works, as long as we offset it with the right combinations of asset A and B. In this circumstance, we end up with an infinite family of solutions with all of them being valid. In the second case, suppose the 0 row has a non-zero number in the rightmost column. So you get a row that reads 0, 0, 0, k for some k that isn't 0. That row represents the equation 0 equals k, which is obviously impossible. So there's no setting of weights that'll actually end up satisfying it. The system has no solution at all, and in portfolio terms, that means that the target exposure profile lies outside of the space that these 3 assets can actually produce. So there's no way for us to form a portfolio that gets us to our targets. So there's 3 possible outcomes for any system of linear equations: a unique solution, infinitely many solutions, or no solution at all. The thing that decides which of these 3 cases you land in has a name, and it's called the rank of the matrix, and the definition ends up being simple. The rank of a matrix is the number of pivots in its reduced row echelon form. In the original portfolio problem, the matrix has 3 rows and 3 columns, and it ends up with 3 pivots. So we say the matrix has rank 3. Every column has a pivot, and that is what we call full rank, and full rank is exactly the condition that guarantees a unique solution when one exists. When 2 of the columns are linearly dependent, the way it was in the modified example, the matrix loses a pivot. It still has 3 rows and 3 columns, but it'll only have 2 pivots when you get to reduced row echelon form. So we say that it has rank 2, less than full rank. And that is the condition that puts you in either the infinite solutions case or the no solutions case, depending on the right-hand side. There is a forward-looking piece worth mentioning here. When the columns of a matrix are exactly linearly dependent, the rank drops and the system either explodes or gives infinite answers. When the columns are nearly linearly dependent but not exactly, the system technically still has a unique solution, but the answer becomes extremely unstable. Small changes in the data produce huge changes in the solution, and that ends up being the cause of a famous problem in regression called multicollinearity. And we'll deal with that in detail when we get to Module 5. Ruth takes her now completed dissertation and submits it. A week later, she gets a letter from her dissertation committee and finds it waiting on her desk. When she opens it, she finds that the committee has voted to reject her dissertation, citing close resemblance to 2 recently published papers in the field. She quickly runs to the library to see what happened. She figures out exactly what these 2 papers were. They're her PhD partner Victor's. Upon reading through them, she discovers the tragic truth. Victor had not just been learning from her, but also stealing all of her ideas. He published them as his own and took the full credit. Defeated and angry, Ruth has no choice but to withdraw from the program as there's not enough time to start a whole new dissertation. So that's reduced row echelon form and Gaussian elimination. We have 3 possible outcomes for any linear system. There could be a unique solution, an infinite family of solutions, or no solution at all. And the rank of the matrix is what tells you which of these 3 you end up in.